Hello, welcome, and an excellent evening. We are back with Let's Code MS-DOS, the series where I present little projects that are coded for MS-DOS in Turbo C 2.0, real mode, 16-bit, VGA, stuff like that. And yeah, we're back making a plasma effect, but this time we did this a couple of years back, I think. This time we're not going for a graphics mode, but we're trying to do this in text mode because the EGA and VGA cards have interesting capabilities in text mode. For example, redefinable character sets. That's what we will use. And the VGA card also supports changing the palette, the EGA card as well, but to a lesser extent. So we can actually use a completely different palette here. And I'm gonna switch down to the main function to walk you through it, and I have a lot of stubs here and a lot of empty arrays that we will have to fill. So hold on to your hats, we are starting now. Well, as usual, we need a couple of run variables. T is, as usual, our time step, so this encodes where we are in the animation. I forgot what I used the CH pointer for. I think I can throw that actually away. That was probably for something different. Anyway, something that we definitely need is this here. This is the palette. It has 16 colors, so 48 entries. And this is basically just a subsampling of the fire palette that we're using for the graphics mode. It does the same color ramp from black to red to yellow to almost white, and looks quite nice for visual purposes, but it's subsampled to 16 colors. The 16 colors can be set directly on the VGA card because you have to go through the so-called palette registers, which is what we are gonna look at now. We need a mapping for the 16 colors to the different color palette registers, which is pretty straightforward for the first 6. So that's actually a one-to-one mapping. So color 0 goes to register 0, color 1 goes to register 1, and so on, all the way up to 5. So here we are with hexadecimal 5. But then we're not going to use register number 6, but register number 14 hexadecimal. And then we switch back to the normal ordering 0x07. For the 9th color, we are using register 38. And then it's actually, again, pretty straightforward. 3A, 3B. Come on. 3C, and all the way up to 3F. Why that is the case, I have no clue. I think that's probably due to the IBM designers who created the VGA card. So yeah, it's a bit weird. The set palette function is very similar to what we would usually do, but we need this indirection via the palette register. So we're just simply doing a loop over all the text colors, which is defined as 16 further up, and there we go. Something like that. And then we will have to write in every loop the palette index, which is the number of the color that we want to set, and we're actually setting the palette register here. And for the usual 256 color modes, it's just a one-to-one mapping, because there we have 256 color registers on the VGA card, and for the 256 color modes, that's exactly what we're using. But for the 16 color modes, we will have to use this here. And that's actually quite the difference to how we usually set the palette, and then we're writing to the palette data port. All these constants are defined in the VGA header file. So if you need to look that up, that's also from earlier episodes. I will check in all the source code as usual. So there you can look everything up. But it's just a shortcut for one of the VGA ports, 3C8 or something in 3C9. I don't know from the top of my head, but I think that might be pretty similar. The sign table is as usual. I'm not going to touch this. We will use that to create the actual effect. Then we have a bunch of things here. Let's go back to the patch interrupt in a second. We will initialize the sign table. We will set the text mode, which is already done. Then we'll disable the cursor, which is a function I will explain. Then we'll set the character width to 8 to have not 9 column characters as VGA usually has, but instead have 8 pixel characters because it makes for nicer rendering, but you can play around with this. You don't need to do that. This is most obvious if you use the block drawing characters that are something like these. There you see in 9 column mode, which we're currently in, that there's a gap in between those things. And in 8 column rendering mode, there isn't. VGA is usually 9 times 16, while EGA is usually 8 times 14, I think. And switching between the 9 and the 8 column mode does exactly that. The 9th column is always repeated from the 8th column or left blank, depending. For example, for the line drawing characters, like the borders here, you need to duplicate it, obviously. Then we set our custom characters and set the palette. And afterwards, while no key was pressed, we draw the plasma, we draw a little scroller, and we do a page flip so that we don't have any flicker, because text mode supports multiple pages, so we can do double buffering. And then we read the character that was just hit on the keyboard and set the text mode and quit. Okay, so there's a bunch of things. I'm going to talk about patch interrupt later. First, we're going to do the disable cursor. Disable cursor is a function of the interrupt 10, namely the function 1, I think, set cursor type. That's not only for disabling, but to basically set the height of the cursor, how thick it is, basically. And you can turn it off completely using that as well. So let's exactly do that. Where is our dummy code? Here, an empty thing. For calling an interrupt, as usual, we need a union called regs. And a union is basically multiple values rolled into one, because an AX register is composed of the high register concatenated with the low register. And we can address both of these using the union, as you will see in a short second. For example, using the X substructure in the union, I can access the AX register and set it to 0x0100, because AH needs to be 01, and the subfunction doesn't matter because there's no AL, so I could have also set it to FF or something. But instead of that, we can have a look at the DOS header file and have a look at the int86. And there we have it. There's also a structure byte registers in the union regs, which I could have accessed like so. I could have written regs.h.ah equals 0x01. That would have been the exact same thing, and I could have kept the AL register as it is, whatever it was defined with. So according to this here, that's probably fine. And we can do the same for the CX register. So we can do regs.h.ch And CH will have the cursor starting scan line, low order 5 bits. And if you set this to 0x3f, this will basically disable the whole thing. And the CL will be the cursor ending scan line, and we'll set that to 0x00. That should actually already do everything that we need. Does it compile? No, there's still an error because we haven't defined it yet here, the character table, which is okay. I'm gonna disable that just for now. Better. And we actually still have a cursor because I forgot to call the interrupt. And that is totally understandable. So we'll call int86 with the video interrupt, which is 10. And then also we pass the registers as a reference because there's also the output registers, and structs can only be passed that way. And there we go. We have a black screen, obviously, and the cursor has been turned off, which is fine. So now we know how to do that. Let's get on with everything. After we disable the cursor, we need to set the character width. We don't need to, but we want to, because we want to learn how to do that. And there are following things that we need to do. That's a bit of low-level VGA programming. We need a temporary variable that we need. We call it x, and x will be filled with a byte that we read from the miscellaneous output read register, and we end that with 0xf3 because here we are selecting the bits 0, 1 and 6 because we need to preserve those. Those have to stay however they are. You can look up all these things and registers in different books, but also online in the VGA and SVGA video programming manual. And the miscellaneous output read register, let's quickly look it up in our VGA header file. The output read is 3cc, miscellaneous output read. Here we go. The miscellaneous output register is being read via 3cc and being written to via 3c2. And the bits are the IO input output address select, the RAM enable, and the horizontal sync polarity. That needs to stay basically. So that's what we are keeping. Then, as you can see, there is also the clock select, which defines, for example, if we are in a 640 or 720 pixel mode. 8 columns is a 640 pixel mode, obviously, because 8 times 80 is 640, and 9 times 80 is 720. And that's basically what we need to set bits 2 and 3. So that's what we're gonna do now. If width equals 9, we want to switch to a 720 pixel thing. So we turn the appropriate bit on, XOR equals 4, sorry. And we are writing that to the MISC output register, and we're done with that. After this, we are disabling all the interrupts. We're gonna enable them a little while later so we don't get any issues of flicker or weird behavior due to an interrupt happening. Then the next step is to go to the sequencer, and the first thing is we're gonna select it to reset. You can look that up as well. And we are also going to reprogram the sequencer to do equally 9 columns, because it has to know about this as well. So this is really a bit more intricate as usual. We are going to look up this particular setting in a moment. So we're going to go back here to the sequencer registers, and we are selecting which one here? I think we're setting the clocking mode register with index 0, 1. That should be the low byte. And there we set or delete the 0th bit, which is what we're doing here in the high byte. With equal 0 is obviously complete garbage. I wanted to have a 9 here. Exactly. 0 selects 9 dots per character. Yeah, that's correct. That's in the high byte, and that's fine then. Okay, that selects this one here. And there's also one more thing, the character map select register, where you can select which character set is being used. We're gonna reset that as well, just to be on the safe side. And we basically select character set default 0. Everything 0 is, I think, default, so that should be good. Then we need to make sure that the attribute controller is in read mode, I think, and to actually enforce that, we read 1 byte from the input status register, which toggles the attribute controller to be in read mode. Because the attribute controller is a bit weird, it doesn't have read and write ports, for example like the miscellaneous output register, but it has a flip-flop basically that toggles between reading and writing, and you can force it to be a certain way by reading the input status register, which is completely weird, but that's how it works. So first we're gonna store the status that we do have in there. So we read from the attribute controller and save that into our temporary variable. And then we're gonna write to the attribute controller. And we're gonna write the value 0x20. And we will turn on the pixel panning register bit, basically, and we can have a look at the attribute controller. So the way that this works is we have to set bit 5, which is the 20 hexadecimal, to 1, otherwise we are going to use the palette address source, but we don't want that. Basically we have to set this bit to 1 and then use the lower 5 bits to set the attribute register that we want to manipulate. And for the case of the pixel panning, it's 13 hexadecimal, which is what I defined this constant to be, basically. So writing 0x20 or pal panning selects the pixel panning register so that we can write to this. This makes sure that the pixel panning is correctly aligned, basically. And we need to, well, it's not explained very well here, but we need to write 0x08 in here, which means 0 pixel offset. Interesting enough, 0 isn't the 0 pixel panning offset, but 08 is. Basically it's 8 minus whatever you write into this, if I remember correctly. So you can play around with this and have the screen shift around a little bit up to 8 pixels. Also quite nice. I think I'll do another video about that feature in the future. And then we have to restore whatever we found previously in the attribute controller, so we'll do that. And we will toggle the latch again, or the flip-flop, so that it's back into read mode. So I think that's good enough here, and we're done with that. That should also do the trick. It has a couple of errors because I forgot something, it seems. Oh yes, that should have nothing like that. There's another error here, undefined panning. Yeah, okay, that was just a typo. Okay, we're good to go. And if you notice, take a look at where my mouse is right now, and if I run this, suddenly the window becomes smaller because we only have 640 pixels. It's hard to see with a black screen, but it definitely gets smaller, so we definitely switched to a 640 pixel mode. That's good. Okay, long story short, we need to set some characters. We need to define custom characters. How do we do this? I will have a function called set characters, and it's just a thin wrapper around the other function actually, so we don't need to call it from the main function. We will call define characters with the number of characters, the index where we want to start redefining, and I chose arbitrarily 128, so we still have all the basic ASCII characters to play with. Then it wants to know which character table we replace. We will replace character table number 0 because you can have multiple character tables on the VGA card, and in a future video I might also show you how you can use 2 at the same time, which is an interesting feature. And we have a certain height and a certain height of the characters and a certain length of the whole table, that is how many characters are in there, and we have the character table itself. That is not actually filled yet, and my idea was to define those characters in 2 squares that are getting larger and larger. Basically, the very first one will be only 0, so the height is 16, so I need to copy this, if I can do it correctly, 16 times, 1, 2, 3, and that's a bit annoying. Oh, okay, let's skip these spaces. Who needs spaces anyway? So now we have 4, 8, 12, 16. So this is 16 characters. And we have 5 different squares, so I'm gonna copy this 5 times. So every line represents 1 character, and every bit represents 1 pixel being set. Right now the first square is empty, which it should be. It's like a space. And then we're gonna go into the middle and pick almost in the middle 2, or right in the middle 2 values. So there should be 1, 2, 3, 4, 5, 6, 7, 8 exactly. 8 to the right, and I'm gonna draw a little square in here. If you translate the 0x18 from hexadecimal to binary, then you will see that the middle 2 bits are set. You have 0, 0, 0, 1, 1, 0, 0, 0. So this will be a little square with 2 pixels on each side. And the next that we'll do is 3C. That is a slightly larger square with 4 pixels on each side. And then we'll have 7E, and that will be 6 pixels on each side, which means also that I have to put in 6 values. And the last, because we have 8 characters, 8 columns per character, it will be FF, obviously. And this will be 8 pixels on each side. You can generate any kind of custom character this way, use a character editor or something and convert that to binary. Let your imagination go wild and produce something interesting here. That should do the trick as well, but we haven't defined the character yet. And now comes a whole lot of interesting stuff. We don't need to program the VGA card directly because there is a function for that, and I have to think about it. I think it's function 11. Exactly. Function 11 of the graphics interrupt is character generator routines user character load. That is AH is 11, AL is 00. It will take the number of bytes per character. It will take a table in character generator count of characters in the table, ASCII code of first character defined, and there will be a pointer in ESBP to the user table. And this BP will become very interesting. All right. I'm going to code this at first in the usual manner. The usual DOS interrupt function int86 doesn't have anything in the word registers to write to ES or BP. It's just not possible. As you can see, we have AX, BX, CX, DX, SI, DI, C flag and flag. So it's not possible to do it like that. However, there is something else in there. Let me quickly see. Which is called the function int_r, interrupt, that has a different structure called regpack. I don't know why they did it like that, but the regpack function supports RAX, RBX, and so on, and it definitely also supports RES and RBP. Those registers together with the DS register were not usable from the other interrupt function. So we're going to use that. We are going to define a regpack structure called regs, and we will fill it with all the good stuff that it needs to be. So we learned AH needs to be 11 and the subfunction is 0. Then the next thing is BX. We will have the number of bytes per character in BH and the table in character generator VL. So we will take the height, which is the number of bytes, shift it by 8 to the left to get to BH, and all this with the table parameter. All fine and dandy. And then we write to CX. That's just our N, and RDX is our C. Last but not least, the pointer. We can take that by taking the segment of our variable, I think it's called buff. Yeah, it's called buff. And the base pointer will be set to the offset of this pointer. Okay, that sounds pretty decent, doesn't it? Well, let me demonstrate this. Let me demonstrate this in the following way. I'm gonna put something here. I will just write printf, and I'm gonna put in 120, can I do this? 128, 129, 130, 131, 132. Those should be the characters that we redefine. However, if we do this, it looks very terrible. The flickering is due to the double buffering, and there's nothing on the second screen yet. It's totally garbage. The reason for this is strange. There's a bug actually, and I posted this on Mastodon. Actually, you can follow me there. I'm root42 at chaos.social. This is mostly the only social media that I use, so please come over and follow me. And Charlie, who is actually a patron and also very much into retro stuff, and he organizes a lot of things around demo parties, taking care of old hardware. He saw this bug and thought he could fix it. He figured out after a long time that there's actually a problem with the code generation in TurboC, and they are generating a wrong offset looking into the rackpack structure basically, and they load the BP register not correctly or not at all. I'm not quite sure. I think probably not correctly, and it points to garbage in memory. So he wrote a little interesting function called patch interrupt, which overrides the int_r function and patches it by replacing 1 byte in the sequence, because you need to look for C6, 46, F4, E2 in memory, and change the E2 at the end to DE, and this will generate the correct offset and it will fix everything. So let's do that, and that's totally magic, and it's awesome that he disassembled everything and managed to fix it. That's why we got this patch interrupt function. So basically we need a running variable, we need to have the patch that can be defined very simple by using hex values in the string C6, 46, F4, E2. And what I find most amazing is that this software is 35 years old and it finally got patched after 35 years. It's awesome. And then we get the pointer to the function. You can just manipulate all the functions, which is very nice, by doing this nice far pointer cast and just taking the address of the function. And now inside of this function it will search for the pattern very simply, and it will do something like this. If we find a match by doing a man comparison from the current pointer to the patch of length 4, and if this results in 0, then it means yeah, we found a perfect match. Then we are going to replace the 4th byte, which is P of 3, with 0xDE, which is the correct offset. And we can print something out. We won't see that, but this will give something for the user if we don't clear the screen beforehand. But we won't see it because we clear the screen right away. But this is the way to do it. And we'll say at which address we patched it, and also return that if anyone wants to check on the calling side. And otherwise we just increment and go through the whole function until we find our patch thing. And if we don't find a match, then this is already a patched version or we can't patch it. So we return -1. Let's build this, looking good. And suddenly we get our squares, our custom squares. You can see that. Brilliant. Now it's fixed. And as you've seen, I put this into something called an ifdefguard, use int_r. There's also a different way we could have done this. We don't need to use this interrupt. So I'm gonna put this in here, use int_r. And there's another way. So we'll do that. But this other way means we can't use the IDE anymore. So I will stick to what we have, but I'll write it down anyway. We can use inline assembly. Works the same way. but then you need to switch to the command line compiler, because TurboC 2.0 can't do that. The later versions can, but this one can't. Basically, we're just loading the registers the old-fashioned way, and it's working just fine. Then you don't need all this magic patching. But I think the patch is actually so cool that I will leave it in. I like to see this great software being fixed basically after such a long time. Something like this. The XORing actually clears the thing, is basically the same as MOV ch,0, but a bit shorter regarding the opcode that is being used. So it generates smaller code. And LES loads ESBP with the pointer, which is also a nice shorthand and much shorter than any other code that I could type, and that should do the trick. That's the same code, but you can't compile it from this IDE. Okay, we've got a lot already going. I'm gonna delete this now because we are ready to draw the plasma actually, or the scroller. Depends on what we want to do first. I'm gonna draw the scroller first because that's more interesting, because we already did a lot of plasmas in our days. So I'm gonna define a static variable that doesn't change from call to call, called time step, which is VGA width times 2. And yeah, that just slows down the scroller a bit. So yeah, otherwise I would just use the time index itself that we're using t, but I can't do that. We need a bunch of variables called index, x, for length, offset, which is half of the time step, so shifted to right by 1. Then we need another static variable for the y coordinate, and I'll set that to the middle of the screen at first, but it will be randomized. The length is the string length of the text. Very simple, so we don't have to recompute it all the time, because we use it a couple of times. We could make this also constant or just pass it to the function. You can probably do some improvements here. Then we count down the time step, and we have an offset into the string, basically, no, into the screen actually. And if that gets smaller than minus length, which would mean that the whole scroller text moved out of the window to the left, because we're scrolling from right to left. And if the offset gets too negative, we left the screen, and then we will need to reset our time step to make everything appear to the right again, and also create a new random y position from 0 to 24. So every time this thing gets out of the screen, it comes back in at the other end at some other position. Then we need to iterate over the x coordinate to draw the actual scroller. We will take the maximum of 0 and offset. So we actually start on the screen and not to the left of the screen if it's running to the left side out of the screen. And we draw this until we reach at most the VGA width, which is 80, right? We can't go further than the right edge of the screen. And the actual position that we end is offset plus the length of the text. Offset is always the starting position on the screen or to the left of the screen if we're scrolling out of the screen. And then we just increment x and then we write to the VGA buffer directly, and the first thing that we write is the actual character to the position x plus y times VGA width plus the back buffer page, because we're writing to the back buffer in our double buffering context, times 2, because every character takes 16 bits in text mode. 1 bit is the character, 1 bit is the attributes like foreground and background color and blinking, plus 0 so that it looks nice, because we are currently writing to the character. And we take 1 byte from the string at position x minus offset. That's our indexing. And then we are also writing the attribute at the same position. We probably also could have used a pointer and increment that. Probably would have been a bit more elegant. And we simply write the color white, or whatever is currently the white color. This should do the trick, and there we go. We're still doing a little bit of a trail here because we're not clearing anything, but this will disappear once we draw the plasma. So this is trailing because there's no space at the end, but only the tilde. Yeah, but the scalar itself works, kind of. The draw plasma function is as usual. We know what this looks like. We can actually copy the printing routine here to our set pixel. Actually, we could have used set pixel here, but yeah, we didn't, so I'll copy that. This will be which we'll take the color as one. We interpret the color also as our shape that we want to use, and we started at 128, and we will use colors from 0 to 4. So 128 plus C divided by 51, because we will actually get colors from 0 to 255, and 255 by 51 is exactly 5. So we will get something from 0 to 4. And the color here we'll mix very interestingly. We will use combinations of background and foreground. C divided by 16 plus C divided by 32. Left shifted by 4. This is the background color. We will have 256 divided by 16, 16 foreground colors, and 256 divided by 32 is 8 background colors. So that's already pretty neat. Does work, but we need to implement the plasma drawing, which we did already before. I won't explain it in detail, but we need a bunch of variables. We need the final color, and we need a lot of intermediate values called C1, C2, C3, C4. Yes, and V1 and V2, which are the sign values that I will cache inside of these. Plus we will need index variables I and j, which we'll iterate over. And V1 will be equal to the sign value at position t modulo 256. Otherwise we run out of the sign table, which we won't. And you can play around with these parameters and make different patterns, but I found these to look pretty nice. 32 plus t times 2 modulo 256, don't forget this. And then we're gonna iterate y from, j from y position, j smaller than y plus the height, and j plus plus, that's great. And for the y coordinate we already take a color value or a sign value to modulate of j times 6. This gives us a higher frequency basically, plus t to animate this. Again, modulo 256, never forget that. And for I equals x, I less than x plus the width, plus plus I plus plus, doesn't matter if you do it this way or that way. And inside of that we define C1 equal to I times 5. And as I said, these are all things that are tried out that do look good, but you can try to find better ones, especially the part that tries to produce a rotating bar. I'm not very happy with that because that's just flipping backward and forward, but I want to have like a full rotation would be nice, but I didn't manage it in time. And C2 is I times V1. This I think produces some kind of rotation, plus J times V2 divided by H plus 2. Yeah, you don't have to understand that right away, but you can turn on and off these components and view them separately. Just use one of those components to plot. Make sure to normalize correctly because we have now 4 components and we'll divide by 4. If you only use one component, don't divide by 4. Otherwise it will look weird or too dark or whatever with too little information there. And C4 equals sine, and that's I think almost the same, so I copy it. That was just a minus to generate something akin to a rotation, and then the whole thing is cast to byte, and I'm gonna just add up C1, C2, C3, C4 and divide everything by 4 or shift right by 2 bits. And then we just set the pixel at this position, I, j, c, and that's it. Yeah, so make sure to try all the different color values here and just use one of them without shifting, and then you can debug what the things actually look like. And there we go. That is the plasma, and I think that looks actually pretty nice, especially the squares getting larger and smaller with the intensity of the color basically. And these are redefined characters in 8 columns. So you now know how to do that. And you see the trading is gone because first we draw the plasma, then we draw the scroller, and on the back buffer everything gets overdrawn by the plasma again. This is currently running emulation-wise like a 486 or something, but I guess this will also run pretty decently on slower machines, as we have way less pixels than in the graphics mode. And that's pretty neat about the text mode. You can do quite nice effects without having to draw all the pixels by hand, but the character generator will draw like a ton of pixels for you just by looking up the value and mapping it to a user-defined character. And that's pretty nice. Let's quickly have a look how this would look when I take out C1 and C3, because those are the C2 and C4 are the ones that are for the rotation. Oh no, they're not. They're actually these wobbly things. I thought I tried to do a rotation with that. Interesting. Let's look at each in turn. C4 looks like this. Yeah, this is like kind of a rotation, but it only rotates like a little bit and is also modulated by a sine wave in its size, let's say. C2 is very similar, but leaning to the right instead of the left due to the different operator, like minus instead of plus, I think. C1 looks like this. This is basically just horizontal bars moving across. And we could also modulate those in frequency, but we don't. And C3, let me guess, is probably vertical bars. Yeah. And everything added together gives us the nice result you just saw. Times 2. Okay, but that's it for today. You learned, I think, quite a lot. I loved the interrupt patching that Charlie did. That was actually pretty wild. And it does help programming. Turbicy, I must say. There are only few interrupts that require ESBP to be loaded, but there are a couple of things where you need to load strings and stuff like that, pointers. So it's pretty nice to have this patch, and it works. It doesn't even patch the compiler, but it patches the runtime. This code is in the executable, and it will patch away the bug from the runtime executable. And that's pretty wild. This is like self-modifying code, basically, in a very simple form. But that's it. Leave a comment, like, share, subscribe, all the usual stuff. Visit me on Mastodon. There are a ton of nice people on there. Root42 at chaos.social. That's where I am. I post all kinds of stuff, or boost stuff, retro-related. Not retro-related at the moment. The advent of code is running. And you will find a lot of other nice people, such as Charlie, and tons of other retro people on there. And the best thing is there are no advertisements, there's no tracking, everybody is mostly friendly, and if not, then you can just ignore those people. But that's it for today. Thank you very much for watching, and I'll see you soon, I hope.